All right, so this is going to be a quick video, I hope. There's a couple examples that we need to go through on Hess's law, and that's going to be kind of the bulk of the video. But just as a little bit of a heads up, this chapter and this kind of unit is about getting energy out of stuff. So harvesting energy, because our entire society functions because of the fact that we can take energy of one form and turn it into energy of a different form. So think about like driving a car. A car, when it's moving, has kinetic energy. It's the energy of movement. How do we power a car? Well, the traditional way of doing that is by putting gasoline in it. Why? Because gasoline has lots of energy stored up inside of the molecules. So we call the energy stored up inside of a molecule chemical potential energy. In other words, it's in there. We just got to get it out. How do we get the energy out of fuels like gasoline and coal and natural gas and propane and butane and all that business? Well, it's pretty simple. We burn them. Burning a chemical that has a high amount of potential energy releases that potential energy, and instead of it being potential, now it is thermal kinetic energy, also known as heat. And at the end of the day, if you remember your combustion reactions, the two molecules that we generally make, it's not always going to be CO2, H2O. Sometimes it'll be carbon monoxide, CO, and H2O. So, whenever we burn a high energy fuel molecule like butane or propane, we take the potential energy and we turn it into kinetic. Generally, it's going to be thermal, aka heat. So this is a transformation of energy. We're taking one kind of energy and we're turning it into a different kind of energy. So like inside of your car, when you fuel up, when you gas up, and then you run your car, what's happening is there is oxygen inside of the engine cylinders, and there's fuel that's sprayed into the engine cylinders. There's a spark plug that initiates a combustion reaction, which is a form of exothermic or energy releasing reaction. All of your octane gets combusted, gets burnt, turns into carbon dioxide and water. Hopefully just that, although we know other stuff goes on in an engine. But the big take home is we get a whole bunch of thermal energy, which means that these products, they don't have a lot of potential energy now, but they're super hot. They've got a lot of thermal energy. And that thermal energy, since these products in a combustion reaction are gases, CO2 bracket G, it's a gas. H2O bracket G, it's steam, not liquid water. Since those guys are super hot now, they expand really fast. And that expansion pushes on the piston head inside of the cylinder, and that moves it. We just turned the energy that used to be stuck in a fuel as potential energy, we turned it into, now it's pushing on an actual object. It's moving something. So now we got kinetic energy. That goes to the crankshaft. That makes your car go. The opposite kind of reaction is endothermic. That's an energy storing reaction. These kinds of reactions start out with low energy product or reactants. For example, a good example of an endothermic reaction is the one that plants do, photosynthesis. Plants take carbon dioxide from the air, they take water that they've collected from their root system. They take those two low energy reactants, they don't have a lot of energy in them because they're little tiny molecules and the bonds don't contain much energy. And they do this series of chemical reactions, overall it absorbs energy. Where's the energy for photosynthesis coming from? Mr. Sun. So the reactions are set up in a way, and you might remember from Science 10, but you probably don't, inside of these little tiny baggies called chloroplasts that are inside of plant cells. And those chloroplasts, they absorb sunlight energy. So that's electromagnetic waves from the sun, light. They absorb that energy and they use that energy to build a certain kind of molecule called glucose. Amazingly enough, animals take that glucose, and so do plant cells, and they break it down again, and they get the energy out. So cellular respiration is actually very similar to a burning or combustion reaction. They're both exothermic, they both release energy, and they both make CO2 and H2O. So how do we figure out how much energy it's going to actually yield? How much energy are we going to get? So here we're actually going to learn the skill of Hess's law. Hess's law is extremely simple. I should go back to the other one here. This looks like an absolute nightmare, but it's really not. If you know how your bank works, you know how you have debits and credits. Debits when you spend money, credits when you deposit money. So if you ever want to find out, what your balance is, and the bank does it all for you, but if you want to figure it out, you take the amount of debits that you, like the amount of money you've spent, and the amount of money that you've deposited or made, and you can figure out what your account balance is going to be. This is the same thing, only it does the calculations using energy. So all this means, we're going to take the total amount of energy in the products, and we're going to subtract the total amount of energy in the reactants. All of this is based on the balanced chemical reactions that we have for the different reactions. I'm going to give you, and in your question pack that I made, I balanced all the reactions for you. So you don't have to balance a thing. You just need to know how to operate Hess's law using our table of heats of formation. Here's something that's a little bit weird, but it kind of makes sense. A negative delta H is exothermic. So the reason why is because if you look at our reactants, they're high up on potential energy, and then they crash. The products are very low. So that's why it's a negative number. So when you're doing combustion reactions they're going to give off energy, they're going to release energy, your number is going to be a negative number. For reactions that absorb energy, they have a positive delta H. If you look here, endothermic, we're going up in energy, so that's a positive delta H. So I'll show you how this works. So let's take a look at the complete combustion of propane. We've already balanced the reaction. It's great. What I need to do is get all of the energy combined in from the products, and then subtract all of the energy in the reactants. So all I do, I'm going to start with the carbon dioxide. I look on my sheet. Hey, look, it's carbon dioxide. How about that? And it turns out that making 1 mole of carbon dioxide costs minus 393.5 kilojoules. So that would be negative 393.5 kilojoules per mole. How many moles are we talking about? 3. So I say 3 mole, and then how much energy a carbon dioxide is worth. So minus 393.5 kJ per mole. Then we have to add the water. This is something that people who don't pay attention are always going to screw up. Combustion reactions are always making H2O bracket G, not H2O bracket L. Therefore, you gotta use the right one. They have a different amount of energy. The reason why, it takes a different amount of energy to make steam compared to making liquid water. So we have 4 mole, and the cost of 1 mole of water as a gas is minus 241.8 kilojoules per mole. So minus 241.8 kJs per mole. And there are my my products. Now I'm going to subtract, and here's the nice thing. Elements, like oxygen is an element, O2 gas is an element, it's free. It actually doesn't cost me any kilojoules. So I could just cross it out. So now I just have to subtract, and I'm going to get the energy for propane. So propane has an energy of minus 103.8 kilojoules per mole. How many moles of propane do we have here? Just 1. So I'm going to say 1 mole, and then I have to put in minus 103.8 kJs per mole. So now I can do this math. Here's another thing that students who kind of are not on the ball, they screw up. Always check to make sure that you're doing these numbers right, because look, we're subtracting a negative number. Why am I mentioning this? Because even kids in grade 12, actually way more than you think, even in Chem 30, the quote-unquote harder course, kids screw this up all the time. You just have to pay attention. Really, that's all you got to do. So let's take a look at what we need to do. So 3 moles, so mole cancels out mole, mole cancels out mole, mole cancels out mole. Which means that at the end of the day, all of these are going to be in kilojoules, which is right. That's what we want. So we have 3 times minus 393.5 plus bracket 4 times minus negative 241.8, and then minus negative 103.8. So we get minus 2043.9 kJ. So this is for this reaction, that's the amount of energy that you get. So if I burn, and everything works perfectly, if I burn it in a theoretically ideal situation, which is not what's going on in your barbecue, but you know, if you burn 1 mole of propane in an ideal situation, you're gonna need 5 moles of oxygen, and you're gonna produce 3 moles of CO2, 4 moles of steam, H2O gas, and this reaction is going to give off or release 2043.9 kilojoules. It's a crap load of energy. It's a lot. Remember, negative values here mean this is exothermic, and the hot dogs and burgers you cooked last week can attest to that. When you burn propane, you release energy, which heats up other stuff. In the case of a barbecue, that's going to heat up the food you're trying to cook. What about the molar heat? Well, in this case, if you want to get molar heat, you divide by the number of moles that are in front of the fuel. So if I just divide this by 1 mole, because that's the number there, that gives me negative 2043.9 kilojoules per mole. That means molar. In other words, how much does 1 mole give out? In order to explain this a little bit better, I've got a reaction here that has a coefficient, a number in front of the fuel that's not 1. So we got to do this one. We'll do it as quick as possible. So nice thing, I can just kill off my oxygen. You still need to do it when you're balancing the equation, because if you don't balance it right, what's the point? So this is balanced correctly. So I'm going to get my products. So we do the energy of the products. So that's 12 moles, because there's a 12 in front of CO2. We go find CO2. That's minus 393.5 kilojoules per mole. So minus 393.5 kJs per mole. And we're going to add our steam, which is 6 moles, because that's what's in our balanced equation. And how much energy does a steam give? Minus 241.8 kilojoules per mole. So there's my products are done. I subtract. I open up a bracket. Now I have 2 moles of benzene. And benzene is plus 49.1 kilojoules per mole. So we get all that done. Now we just have to do the math. So we got 12 times negative 393.5. We add 6 times negative 241.8. Then we subtract 2 times 49.1. Cool, it actually gives us a really nice whole number. This gives us minus 6271 kilojoules. So that's for this whole reaction. If you want to make it molar, in other words, how much, this is for 2 moles of benzene, how much energy do you get if you're just burning 1 mole of benzene? All we got to do is divide by the number of moles of fuel. That makes it molar. It's per mole. It's just like if you have, I don't know, a roast beef that is like $35 and it weighs 1.6 kilograms. You're like, well, how much is that per kilogram? You divide by the kilograms number, and that will tell you the cost per kilogram. Here, this is the energy amount per mole. So we divide by 2 moles, and that gives us negative 3135.5 kJ, and now it's per mole. So sometimes you're going to have a number out front in the fuels, a coefficient in front of the fuels. If you want it, when you calculate the energy, that's the total energy of the reaction. If you want the molar, you divide by the number of moles. Hope that clears some stuff up. You do have a couple of these Hess's law questions on the question pack that I gave you. There are also more examples in the book. Just keep in mind you're taking the coefficients and multiplying them by the energy cost of that molecule. And you always go products and add those up and then subtract all of the reactants. And remember, you get to cross off oxygen because it doesn't count.